Hi, everyone. I'm really excited to be here and share some of our recent research with you. My name is Fei-Fei Li. I'm a Sequoia professor of computer science at Stanford University and also co-director of Stanford Institute of Human-Centered AI, Stanford High. Okay, so the topic of our conversation today is from seeing to doing, understanding and interacting with the real world. I want to take you back 540 million years ago. And what is it life like? At that point, animals lived in the primordial soup of a younger Earth. And most importantly, there aren't that many animal species. The world is relatively simple. You're seeing an artistic rendering of this. And then something remarkable happened in geologically a very short period of time. And that's what zoologists and evolutionary biologists would call the Cambrian explosion. During about 10 million years, which is a very short amount of time, the number of animal species just exploded. Suddenly, the very laid-back environment in the primordial soup of the Earth becomes a lot busier. There are so many animals in different shape and form and doing busy things. So what happened? There are many theories between climate change, chemical change in the water, and other theories. But one of the leading theories is very intriguing, and it was proposed by Andrew Parker, a relatively young zoologist from Australia. He conjectured that the Cambrian explosion is triggered by the sudden evolution of vision, which set off an evolutionary arms race where animals either evolved or died. In other words, perceptual ability to see and sense the world was the beginning of a very long arc of evolution. And of course, 40 million years later, most of the animals in the animal world uses vision as one of its primary sensing apparatus, and also visual intelligence is defining to animal lives. And humans are no different. We use vision to survive, to navigate, to manipulate things, to interact with each other, to understand the world. It is said that 50% of our neocortex is involved in visual processing. Understanding visual intelligence is key to understanding intelligence. So, of course, I've been fascinated by vision, and I do believe vision is a cornerstone of intelligence. And what we use this cornerstone for, both as many animals, but also especially for human, is to understand the world and to do things in the world. And that is the two topics I want to talk about today, using vision to understand and using vision to interact. I'll begin with a series of seminal studies in recent decades that underscores the powerful nature of human vision intelligence. One study is by Irv Biederman. He showed two types of pictures. One on the left he calls the congruent picture, where the human subjects are asked to detect an object in this picture. In this case, it's a bicycle. You can see it on the lower left corner. The amount of time they have is 150 milliseconds. In the meantime, in randomized trials, the human subjects are also asked to detect the bicycle, the same bicycle, in an incongruent picture. And you can see they're scrambled. But intriguingly, the bicycle itself, or the physical location of the pixels of bicycles on the screen is in the same position. Yet the performance, reaction time and performance of human subjects for the incongruent picture of bicycles was longer and less accurate. So it underscores a very intriguing capability of human intelligence that sees rapidly a holistic scene before it sees any single objects. And in similar vein, in a series of studies called Rapid Serial Visual Perception, RSVP, Molly Potter and other colleagues have found out that humans can detect objects that they've never seen in very rapid and accurate ways. In this case, the refresh rate of this video is 10 hertz, so every frame is only presented for 100 milliseconds. Yet if your task as an audience is to detect a human somewhere in this video, you'll have no problem seeing that frame containing a human. Even though you have never seen this video, you don't know what I mean by human in terms of its shape, clothes, gesture, location. Yeah, you have no problem doing that. And fast forward, in almost the turn of the century, a bunch of neurophysiologists have found and put a time on the speed of visual processing. They used brain EEG studies to measure exactly how fast can humans categorize complex objects such as animals versus no animals, and the use of photo data set. You can see these are examples of hundreds of pictures of animals and hundreds of pictures of distractor images. They're very complex. Yet by measuring the brain waves of humans, the experimenters find out that at 150 milliseconds after the onset of the signal, there is a differential brain signal that shows the categorical difference between a person seeing animals versus a person not seeing animals. Again, this is underscoring how rapid and robust our visual capabilities are. Last but not the least, I want to share with you a study I did at the end of my PhD, which is almost 15 years ago, where we ask people to look at real life photos for a very short amount of time, and then we quickly mask it with a wallpaper looking mask, and then to type what they see. If the presentation time is 500 milliseconds for the picture, it's like eternity. People can write novels depending on how much you pay them, but there's a lot of comprehension seeing the objects, the things, the activities, the mood, the layout, and all that. But even as short as, let's say, 67 milliseconds or 100 milliseconds. These are like literally a blink of an eye. Human subjects are able to recognize objects as things. So seeing is understanding. The ability to see the world and not only to just register the grayscale values or the reflectance or the colors of the pixels, but to making sense of the contents is really critical for humans. And we want to enable computers to do that. And what is a critical understanding task? If we go back to this experiment we just shared, you recognize that humans recognize objects. Calling out and labeling objects in a visual scene is critical to the ability to understand the full picture. So object recognition is a fundamental ability for humans and of course for computers that we would like to make them have. And for those of you who are not familiar with this term, a generic way of defining object recognition is giving the computer a picture and hoping the algorithm can label the picture with its main objects. It's very effortless for humans, apart from the fact that you might be wondering what this cute little animal is. We recognize daily objects very easily. But if you think about it, it's actually not that easy. Objects come into all kinds of shape and forms, lighting, articulation, occlusion, clutter, and all that. So it's really mathematically, there's infinite ways of rendering a single object, let alone a class of object in the 3D world. So this is a daunting task. Now, what have computer scientists done in the history of trying to tackle this problem. In the early days, concurrent with these early pioneering psychology studies, we've got computer scientists who are thinking about designing models. The early days of models are hand designed. They tend to be configurations of geometric shapes, such as geons, or what we call generalized cylinders, and so on. That didn't get us very far other than its great conceptual work. So then around the turn of the century, the problem of object recognition turned from hand-designed models to hand-designed features, but learned models through statistical machine learning. So these are just examples of how the field of computer vision uses hand-designed features like patches, textured patches of images, and try to learn statistical models by automatically estimating the parameters that configure these patches. And there has been some early success, and one thing that has impacted the field quite a bit is the recognition and introduction of data sets and benchmarks. And for example, Pascal VOC or Caltech 101, these are seminal data sets that test machines' ability to recognize a handful of object categories. So that was around the time I became a professor in 2005, 2006, and was really fascinated by this problem and was working on various kinds of machine learning models. But one thing that really bugged me was that the whole field was testing on a handful or a few dozen object classes, whereas the real world truly has way more objects than just a few dozens. In fact, I was very inspired by a psychologist called J.J. Gibson, who really advocated an ecological approach to perception, and someone summarizing J.J. Gibson's position is that ask not what's inside your head, but what your head is inside of. It's really a way to accentuate that when you think about representation and intelligence, not only you want to think about the core task we're doing here, which is visual understanding, but really what environment we're doing it in and for what purpose. And here, our goal is not to recognize 20 objects. Our goal is to recognize and understand the full world, the full scale of the world. So long story short, we went from these traditionally smaller scale data sets to our project ImageNet, which we assembled 15 million images across 22,000 categories, and really tried to start pushing the field towards that kind of large-scale object recognition through ImageNet Challenge. And of course, everybody knows in 2012, Jeff Hinton and his students published the paper ImageNet Classification and Enter ImageNet Challenge using convolutional neural network. And that was the year that this winning model showed tremendous progress in cutting the errors down of object recognition algorithms. And since then, the field's progress has just been enormous. In object recognition itself, we've been seeing winning algorithms of ImageNet Challenge and related tasks every year, producing incredible results. And not only algorithms have been advancing, also, you know, the kind of the size of the work of the algorithms and the efficiency of the algorithms also have been advancing. So it's really very exciting since 2012. But of course, when it comes to visual processing, understanding, visual understanding and perception, there's a lot more beyond object labeling. For example, if there are two pictures, both labeled as llama and a person, it feels like they must be delivering the same story. In fact, they're very different pictures. One is a llama standing next to a person, the other one is chasing a person. So a psychologist, Jeremy Wolf, once said, one could imagine objects would be sufficient to categorize a scene, but it's not necessarily true. Relationships between objects must also be coded as part of the story of the scene. So going beyond ImageNet, our lab has done some work in encoding relationships through a scene graph representation. Here, given this image, the pink boxes you see are labels of objects like cake, person, camera, a doll, earring, and all that. But the green boxes you see are relationships between these different objects, from eating to left off to feeding to holding. And then the blue boxes or purple boxes you see are attributes like the color of the dress and the mood of the person. And all this is a scene graph that represents a deeper story of the image. And we put together this data set and benchmark called Visual Genome of 100,000 images, millions of objects, millions of relationships, millions of attributes, millions of descriptions. And that enabled a whole number of research that works on relationship understanding. One of them is presented here, is visual relationship estimation using a decomposable representation. And what's really nice about this work is that not only it can recognize relationships that are typically represented in the world, like person riding a horse, it also can use the composable representation to learn using zero shot or few shot to learn new novel compositions, like in this case, person riding a horse and person wearing hat are both known relationships and have lots of training examples, but horse wearing hat is unusual. And because of this composable representation, our algorithm is able to recognize this using zero training example. And here's another example of an algorithm have learned person sitting on a chair and fire hydrant on a field, and then it's capable of recognizing person sitting on the fire hydrant with zero training example. Of course, quantitatively, we've shown good progress in tackling this novel composition zero shot learning scenario. And this deeper, richer way of representing visual scene for deeper understanding is actually being adopted quite widely in the field. There has been a lot of work in using scene graphs for different various tasks. We've also extended this to spatial temporal video scene graph in a work called Action Genome, over 10,000 videos and 157 activities. And again, using this representation, we're able to achieve state-of-the-art action recognition as well as few shot recognition. We also went a step further, not only estimating relationships, but also putting all this into a sentence, into a story, and to ask algorithms to speak English to us. So the work here I'm showing is a number of work where the input is a picture like people riding on a carriage or a horse, and the output is either a sentence to caption this entire scene or dense captioning in terms of be able to narrate different parts of the scene, or even generating paragraphs and so on. So that's a number of work related to this beyond object, single object understanding of scene. So that was a very quick overview of what we've done, what I've shown you in terms of visual understanding. What we see here is a number of work that capture different important parts of computer vision research. One is, of course, representation. For example, using scene graph is a powerful representation for scene understanding, but also work in algorithm, in machine learning, deep learning algorithms, and also relationship with language, but also the importance of data and benchmarks, whether we're looking at ImageNet or a visual genome. And at the core, our hope is to create agents or computers that can perceive what the real world is. So our lab has done a lot more work than what I have shown you in this space, but I'm going to actually pivot a little bit now. Traditionally, a lot of computer vision work is actually understanding and perceptual tasks like object recognition, but the real world is a lot more complex than that. And what vision is created by nature is also more than just understanding. This brings me to a philosophical argument of Plato's allegory of the cave. He was pointing out the limitation of our visual our visual ability. He's saying that really the world is 3D, and we're seeing a projection of the world through our retina, 2D projection, a 2D projection on our retina. And it's almost like we're prisoners in the allegory of the cave, where we're forced to look into a wall in front of us, and there is a full play happening in the back of our head and being projected onto the wall. And the prisoners are forced to interpret what the play is by looking at the projection of the world. So that is a pretty contrived description of what vision is. And in fact, visual animals are not tied to a chair, and we're not passively watching the world, even though there is a 2D projection. We're actually participating in the world. So there's more to vision. In fact, if we're only passively viewing the world, there might be a lot of cases of errors. For example, a simple example of a mug. If you're just watching a mug, if you watched it, perceived it in a wrong way, or in a way that is, say, HA or HB views of this mug, it might not be able to enable you to ever interact with this mug in the right way. So there is a lot more going on in the relationship between perception and the organism's behavior. In fact, real visual experience is extremely active and dynamic in the animal world. So here's a quote from one of my favorite books, The Other Minds, is that the original and fundamental function of the nervous system is to link perception with action. And so perception is not passive. And the purpose of perception might not just be to understand and label things, but to act in this world. And many of you know this particular experiment. It's a little bit a cruel experiment coming from the 60s. And the idea is to show that two newborn kittens, they are put in a visual world, identical visual world, because they're yoked together. But one kitten, the active kitten, is allowed to drive this yoke and move its body, whereas the passive kitten was only being driven by the active kitten, and it has no leg movements and very limited range of neck movements. And lo and behold, after a few weeks, the active kitten developed a intact and a normal perception system, whereas the passive kitten had a very damaged or very limited perceptual system. And the good news is after a while, if the passive kitten is experiencing the real world in a normal way, it regains that ability. Also, we found neurons in our brain, called mammalian brain, called mirror neurons, that fires not just by looking at things, but by looking at actions, and it's reacting to that perceptual link with activities itself. So this is a long way of saying that if you look at evolution, the onset of vision is the onset of active animal life. It's also the onset of a long trajectory of more and more powerful brains. So clearly there is a need to connect perception with action. And that's what I'm excited about these days, is to look at computer learning systems, or we can say embodied intelligence systems that have the ability to do things, interact with the world through sophisticated perception and understanding of the world. So seeing is for doing in the real world. So now we want to ask, what kind of doing? Naturally, we gravitate toward robotics and embodied AI. There has been a lot of success in industry structured environment robots, but really the breakthrough that's down the road must be in unstructured environments. So in the recent years, our lab has been doing all kinds of work in robotic learning, from explorative learning to exploitative learning to, focusing on different tasks. And I also want to highlight there is a key missing piece that we think that is lacking in a lot of robotic research, and I want to share with you our latest work. But let me just quickly also show a couple of work in both explorative learning or exploitative learning. Explorative learning is what we really call colloquially curiosity-driven learning, or learning to play. And the idea is how we can train a dynamic world model in a self-supervised way to enable a learning system to form a world model and a self model to learn to perceive the world. And this is what maybe human children have done in their infant years, is to explore without a task in mind and form that representation of the world. Of course, there are different flavors of this approach. There are novelty-based approach, there is a goal-based approach, and world model-based approach. And ours is more a world model-based approach, and we're especially inspired by work like forward dynamics and inverse dynamics and so on. And quickly, this particular work I did in collaboration with Dan Yeamans and Nick Haber and Damien Maroka. We created an algorithm where the goal of the world model network is to predict the consequences of actions, and the goal of the self model network is to predict the error of the world model, and then the actions every step of the way is the action choices is by the self model that is adversarial to world model. So it's kind of a curious intrinsic motivation that's driving the action choices. And what we get is a emergence of structured behavior. In this case, this blue curve is showing you that in the early epochs of learning, the algorithm is still just learning its own ego motion, and then it starts to pay attention to objects, and then it starts to learn about one object and two objects, and so on. And in a recognition task, the curiosity-driven algorithm performs better than random policies. So that's one line of work. Of course, there's more work in task-driven, or what we call exploitative learning, robotic learning. And most of these learning today are based on skill level tasks and short horizon tasks. And our goal is definitely push for longer horizon tasks. For example, in experimental setting, this particular task called to organize a desktop by putting together these forks and these bowls is what we consider a longer horizon task. In this particular work, in collaboration with Silvio Savarese, Dan Fei-Fei Li, Yuke Zhu, and Animesh Garg, we propose neural task programming to modularize the learning, the composable learning of different short-term skills, so that the algorithm can piece together the learning of a long horizon tasks. And the key idea here is a divide and conquer algorithm to enforce modularity and to ask our algorithm to learn to specialize through divide and conquer in different short horizon skills, and to be able to handle long horizon tasks. And I'm not going to get into the details, but neural task programming shows superior performance compared to state of the art at that time. And we're able to do long-term tasks like these kind of more complex object sorting tasks. And in this case, the goal of the robot is to stack a color block, but it's robust enough to deal with an adversarial attack in the middle of this experiment and learn to reassess the state and complete the task. Another example towards more complex and long horizon task is to actually do some kind of curriculum learning and learn to generate tasks from simple to complex along the way. And this is work with Silvio Savarese and Quan Fang and Yuke Zhu. And the idea is that through these generated tasks, we can learn policies that can handle more and more complex tasks. And our challenge here is robotics tasks like this have sparse rewards, and we have a very large state action space that we have to search through. The good news is that generative model has been, one of the most exciting progress areas in AI and machine learning, and we see generative models in images, in shapes, in languages. And here we ask the question: can we have generative models in tasks? And schematically, we parameterize our task space. If this is our target task, we're able to generate different tasks along the way to with the goal of learning more and more complex policy towards the eventual target task. I'm not going to get into the details of how we parameterized the task space in different dimensions. We created this algorithm where we have a task generator that first learns a procedural generation and generates this task, and then we have a discriminator network compares the target task with the generated task and score a similarity score, and also assess how the algorithm does in the current generated task. And both information gets sent back to the task generator. The goal is that we want to increase the similarity of the generated task and the target task, but also ensure that there is enough of a performance achievement. The reward parameter is relatively high because you don't want to generate a task that's too hard too early. So we do this iteratively, and again we call this work AppGen, Adaptive Procedural Task Generation for Hard Exploration Problems, and this was a publication last year. I'm not going to get into the details of this this work, but here is, for example, we tested on a manipulation task. You see here the target task and the generation, and the generated task. The blue target zone, you can see it was very large at the beginning, so it's easier to learn, and they start to shrink, and also the environment gets more and more complex. We tested this in 3 different tasks, from push the target objects across the bridge, to insert the target object into the slot, to clear the path in order to reach the goal. And we see a advantage of our work over other state-of-the-art work. And okay, so we just very quickly give you a little bit of a flavor of some of the robotic learning tasks we have been doing in our lab, from curiosity-driven learning to task-driven learning, and also emphasizing on learning representations such as task graphs. But I did allude to, give you a teaser, that there are some key ingredients missing, in our opinion, because we already alluded to that most of today's robotic research is skill-level tasks and short horizon goals. And there is, on top of that, it's on artificially simple environments. Even our own lab, when we're thinking about the so-called long horizon tasks, as you could see, it's relatively simulated and contrived. So most of the work is small scale and anecdotal. Tasks are picked by experimenters. There's no particular profound reason that we have to be stacking color blocks or moving one object across an artificial bridge to another object. It lacks standard metrics, and it's very individual lab driven. So with these constraints, you got some real world systems like this, a robot that's trying to put a box on a shelf. It's it's notoriously hard because the environment is real and cluttered, and that means the dream of achieving human capable robots is really quite distant. So having said all this, how should we close the gap? Clearly, we have many directions to go, including developing better algorithms and all that. But we also want to learn a page from machine learning, from computer vision and natural language processing, that important realistic data sets and benchmarks have been driven critical progress in this field. So can we borrow a page or two from this from these fields? So here's a revised quote by J.J. Gibson by us, is, can we consider an ecological approach not only to perception but to robotic learning? So ask not what's inside your head, but what your head and body are inside of. So the point is, how do we create robotic learning environment that mimics the real world as much as possible? So one of the best environments I think that the real world robots will eventually be in, and that's really complex, is household environments. Household environments are ecologically complex, are dynamic and uncertain, have large variabilities, interactive and social, and inherently multitask. And inspired by this, we are rolling out a benchmark called Behavior, benchmark for everyday household activities in virtual interactive ecological environments. Here, I'm showing you a simulation of what behavior environments look like. This robot is being the tour guide, showing us the rendered environment of behavior. And I'll give you a little more details. Behavior is put together by a large team of Stanford researchers and students with the specific goal of creating a robotic learning simulation environment and benchmark that's large scale and diverse, that's ecological, that's complex. The tasks are complex, like long horizon and multi-steps, and have standardized and flexible evaluation metrics. So by large scale and diverse, we include 1,000 activity or tasks. We'll show you how to choose these 1,000 activities. We have scanned 50 large-scale real-world scenes and built digitized the 3D environment over these 50 scenes, 8 scene types, more than 1,000. Now it's actually probably more than 2,000 object categories, 3,000 object models, and a large number of objects per activity. And of course, because it's simulation, it has an infinite number of texture, lighting, configuration, instantiations. And we really try very hard to achieve the goals of photorealistic. It has kinematic and dynamic extended states. It has flexible materials, deformable bodies, realistic fluids, thermal effects, realistic action executions, and object distributions. So I've already given you an overview of what behavior is, but just to dive in a little deeper, one would ask, where did you come up with the 1,000 tasks? That's very different from today's, handful of robotic tasks. Well, we're actually keenly aware of the concern that human jobs are at risk when AI is more advanced. But this concern is also juxtapositioned with the real human needs of taking care of the elderly, taking care of the young, taking care of the sick, and we have a global shortage of labor. So between the concern for human jobs and the concern of taking care of ourselves better, we took the approach, a human-centered approach of taking all the potential tasks that people do through surveys like American Bureau of Labor Statistics, Eurostats, and so on, and curated thousands of everyday activities as candidates, and then did a user study to ask how much would you as a person benefit if a robot did this for you. This is intrinsically getting at the question of what are the tasks that humans would like robots help? And we learned something very interesting, right? Cleaning is by far one of the most important tasks that humans want help, whether it's cleaning after a wild party, or cleaning a toilet, cleaning walls, and so on. But there are also tasks that humans don't want robots to do, such as playing squash or opening Christmas gifts. So we ranked all these 2,000 tasks and took the top 1,000 that humans prefer more robotic or machine help. And we use that to formulate the base of our 1,000 activities, the 1K activities. Now that we have established these activities, we need a user-friendly language to describe what is the initial state of each task and what you want the robot to achieve. And this is what we call the BDDL language, where it's a logical form of descriptions of what the initial state and the goal state of each of the tasks would look like. And to build this BDDL database for each of these tasks, we actually use both human annotation help as well as GPT-3, and we combine the strength of all these to put together the BDDL annotation. So now that we have the tasks, we have the logical form to describe the tasks, we need an environment. We need to specify the kind of environments and features of this data set or benchmark. And we care a lot about the diversity of objects. So we already talked about we have thousands of object models, and some of them have properties like cookable, sliceable, freezable, burnable, deformable, and so on. And many objects are articulated with the moving, opening and closing and different kind of articulations with joints and axes and so on. We also have environments ranging from houses, hotels, grocery stores, restaurants, schools, gardens, halls to offices. And with all these prepared, we need to build an environment to simulate all these tasks to allow embodied AI agents to perform these tasks in this environment. And this is what we set out to do. Simulation is really important. They are fast for training, they are safe, and there can be easier ways to overcome real-world biases and can be reproducible for benchmark. And there has been a lot of wonderful simulation environments built in robotic learning. We're just showing a few here, from Habitat to AI to Thor to 3D World to Sapien and so on. And they both come with its own strength. But what we really want to focus on is not only the ability to interact with the objects, but some of the key abilities like the changes of temperature, wetness, deformability, and so on. So this is just a figure to show that our behavior simulator covers some of the key abilities in this simulated world, and we have officially combined our effort with NVIDIA's Omniverse, so created an environment we call OmniGibson, because it came from our previous work, iGibson. And OmniGibson is this realistic simulation environment where we can simulate thermal effects, transition machines, lights and reflections, fluids, deformability, and transparency. And we actually did a user study on the realism, photorealism in the rendering of these different simulation environment. And here the perceptual, the user score, the higher the score, the more realistic it is. So the users give us a pretty high score for OmniGibson compared to other simulated environments. And I've already shown you one video. Here's another video of what OmniGibson can render with a lot of high fidelity, details, high resolution, and realism. So last but not the least, we can start to evaluate embodied AI algorithms using behavior 1K dataset. There is a long way to go. There's no algorithm today that can perform 1,000 tasks. And we actually just selected very few and selected a couple of state-of-the-art at that time papers to evaluate, to get a baseline understanding of how today's algorithms do in behavior benchmark. One is the soft actor critic deep reinforcement learning paper. The other one is the PPO paper. And we first asked just evaluate the skill level, such as grasping or soaking towel or cleaning stained shelf or cooking meat or slicing fruits. And the bottom line is that if we provide a simplified magic action at the end, our algorithm, the state-of-the-art algorithm can do relatively okay with these short skill tasks, which are the blue line. But as soon as you allow you do not allow that simplified and active action, suddenly it drops to the orange line. And if you increase the object pose and object appearance diversity, the algorithm performance also drops sharply. And of course, let me just start this. Oh. Let me try, and I'm probably just gonna. Of course, it's not enough. Here is a example of RL algorithm trying to decorate a store, and you know, this is where we're trying to show the kind of long horizon tasks that behavior aspires to do, instead of just these short skill level tasks such as grasping or slicing. And again, using a task like this store decoration or collecting trash or clean table, we have to give a lot of assumptions for the algorithm to perform reasonably. Assumptions of, you know, privileged access to the action primitives and the state of the objects. If we relax all these assumptions, the algorithm performs very badly. Pretty much zero performance. And this is kind of exciting because it shows these tasks are extremely complex and there's a long way to go in achieving these tasks. And last but not the least, we are also considering sim to real world transfer. So we have built an apartment in the basement of our department and put our real robot into this apartment, but also created a digital twin of this environment in behavior simulation environment, so that we can experiment on sim to real algorithms and so on. So let me just skip. So this is really the all I want to say of behavior. You can check out the more of this work at behavior.stanford.edu. We're just very excited to create this environment and benchmark that really aims to take robots into the real world environment, and challenge ourselves in thinking about tasks that goes way beyond the simpler, shorter horizon skill set level tasks. And of course, you know, never mistaken a clear vision for a short distance. There is a long way to go. Behavior is really only possible by a large number of PIs, students, postdocs, and the team is still expanding. And overall, this is what's been exciting me, is this missing piece in robotic learning, which is driven by North Star data and benchmark environments like behavior. And, you know, at the end of the day, vision is a cornerstone of intelligence, especially of embodied active intelligence. And our lab's work focuses on this kind of real world ecological approach to both perception and robotic learning. And thank you very much.